So, as Chris told you, I am Alex Stato. I'm a composite strengthening systems field engineer with Simpson Strong Tie. Also have with me today Wendy Allen, who's our field engineering manager, and she's just going to be in the chat. Before I dig in too far, I want to add to the comments my contact information. So if you guys have questions about anything I'm talking about, please add them to the chat with your email. That way, if I don't have time to address them verbally at the end of the presentation, I have your contact and I can reach out directly. Okay, looks like my presentation has disappeared. Hopefully it's back up now.
Yes, it's back up.
Oh, great. Sorry about that. Okay, so today I'm going to talk about the I-90 Homer Hadley Bridge retrofit. And if you're not familiar with the project, back in 2008, Sound Transit endorsed a tax measure that basically allocated money for linking Seattle to Bellevue with some form of mass transit. And the westbound I-90 span was chosen for the route. Westbound I-90 was originally completed in 1989, and it was named for Homer M. Hadley, who was the architect of the eastbound I-90 spans. So the westbound I-90 span is supported on floating pontoons, which you can see in this photo here. Down at the bottom, that's a big concrete boat that's supporting our entire substructure and superstructure. So it's almost like a floating foundation. And this floating portion of the bridge is going to see about 2 feet of deflection seasonally due to the change in lake levels. It's exposed to wind, waves, and even traffic. So it's already under quite a bit of different load cases, and when you start to add on a fully occupied light rail train, which is the system that Sound Transit ended up going with, the structure is actually fairly challenged at that point without a retrofit. So that fully occupied train system is going to be mounted to the side of this floating bridge, and the bridge needs to be retrofitted to support that entire system. That occupied train is enough to make the pontoon sink even another several inches. So there's a lot of movement involved in this large concrete structure, and a lot of design went into working around that movement and making sure that the light rails could operate correctly. So the pontoons themselves were strengthened using tensioning strands, PT cables, and that stabilized the movement. And then the substructure itself needed strengthening for vertical and lateral forces due to the new light rail system. And this presentation today is going to go over how FRP helped reinforce the supporting bents in the pontoon system on the westbound spans by 90, and hopefully teach you a little bit about how FRP is used and how it's applied. So for those of you that are unfamiliar with FRP, it's a composite strengthening system, meaning that it works with the parent substrate, in this case, a concrete bridge structure, in composite to reinforce that substrate and bring it up to a higher strength than it was prior to the FRP application. So what is FRP? The FR is fiber reinforcement. In the case of the Homer M. Hadley Bridge, it's actually carbon fiber reinforcement, but glass fiber is also prevalent in the industry, and aramid used to be used kind of earlier on in the FRP range, but carbon fiber is stronger and cheaper, and then glass is much, much cheaper, so you can address most projects with just carbon and glass, and aramid's kind of fallen off the wayside. The P is going to be a polymer resin. That's commonly epoxy. There are vinyl epoxy saturate or vinyl saturants as well, but epoxy bonds well as a concrete. So that's the polymer resin that's generally used in reinforcing concrete and masonry structures. So FRP is going to be designed, kind of governed by 3 main documents. ACI 440.2R governs FRP applications on concrete structures. ACI 440.7 governs FRP placed on masonry structures, and then AASHTO LRFD bridge design specifications lists measures specific to highway applications. All right, I was very quickly going through what FRP is, and now we can talk a little bit more about the project. So I'm going to focus on the substructure at first. The FRP retrofit was focused on certain elements of the substructure. So if you're looking at this screen, we're looking at the actual columns in the bent supports. And it's a seismic retrofit of this portion of the bridge. The EOR was KPFF with Sound Transit and Washington State DOT. The FRP installer was FD Thomas Structural Specialties, and the general scope was shear strengthening of existing columns. So these columns, they needed a higher shear capacity in order to take lateral forces on the vents and make sure that these concrete columns aren't going to fracture under an event. And we did that with FRP. You can wrap the columns, which in itself will bring up the compressive strength by confining the concrete. And that higher compressive strength will give you a little bump in your shear strength, but the actual FRP reinforcement itself, wrapping horizontally around that column, works very similar to a rebar tie, closed tie, and can be used for shear reinforcement as well. So it's actually, if you're looking left to right where these arrows are, the portion at the top and the bottom of this column section would be working in shear, while the portions running vertically are helping to confine that concrete, bring the overall strength of this whole column as a composite section up to where it needs to be to resist those lateral forces. All right, and now on this photo, I want to start talking about how FRP is installed, because FRP is going to be very dependent on whether or not it's installed correctly, and it needs to bond well to that parent substrate. So it's kind of a simple process, and as long as you take good care while you do it, it can go very, very smoothly. But essentially, you need to take off that top layer of concrete that's smooth and buttered out, remove that, expose all the pores of your concrete, and that'll allow our epoxy priming coat to seep into the concrete. And that's essentially the process. You would prep the concrete to open up the pores, come through and prime it with an epoxy saturant. Then you go back over one more time with a thickened epoxy paste. That will fill in any imperfections in the surface, any bug holes, make it nice and flat for FRP to be installed. And then you can saturate and apply your FRP to the outside of the column. Some things that are a little bit important to note is FRP does not want to go around a hard corner. It can, but it's not going to go well. That hard corner has a chance of cutting your FRP. So when you go around, say, the extreme corner of a column, you're going to radius that corner in order for the FRP to make that transition without getting split by the hard corner. Another thing to look at is this is an exterior application, obviously outside. Up here in the Pacific Northwest, we get some cold days, and because of the epoxy component of FRP, you're going to want to make sure that your substrate is 45 degrees or warmer in order for the epoxy to cure. Anything under 45 and your epoxy is going to hold off its cure, and at that point you're not really sure when it's going to cure out correctly. So we always make sure that the substrate's brought up to temperature at least 45 degrees or greater, and then on the high end it can go all the way up to 95 degrees. Now, going back to how important surface preparation are, and the reason for that is that we're trying to get FRP to work composite with that structure. So they're all one piece working together, and we're not looking at it as an individual element anymore. And the substrate preparation is all there to ensure that you get a very nice, efficient bond to your substrate. So in these photos, we're looking at a pre-construction or pre-installation adhesion test. Where they apply these test dollies over to the concrete directly, let them cure up, and then eventually pull them off the substrate to show that they're getting a 200 PSI bond. And if you look very closely down here, you can see they got about 307 with very little substrate prep. So they are in very good shape for this project to apply FRP, and they know that that concrete is sound enough to actually apply FRP onto. This is actually going to be one of your field testing requirements after installation. So once all the FRP is applied and cured out, they would come back through, apply these dollies, and then pull directly through the FRP all the way into the substrate to prove that the system is bonded at that 200 PSI top to bottom. And that's one, really the main field test that's conducted. There is laboratory testing that accompanies FRP projects. And that's going to be ASTM D3039, which is direct tensile testing of an FRP sample. So when you're on site installing FRP, the installers will create 12 by 12 witness panels. Those panels will get cured in the conditions on site and then shipped to a lab. In the lab, they cut them down into tensile test coupons, put them in a tensile testing machine, and pull them to failure. And that testing is required to prove that your FRP is properly saturated and meeting all of its design properties. The direct adhesion test is actually ASTM D4541. So still looking at the columns, FRP, in order to function correctly, has to have full saturation of the fiber. So when it comes out to site, generally it is a woven flexible fabric with no epoxy involved whatsoever. And then you're actually saturating it with the epoxy, dipping it into a bath, working that epoxy down into the fibers so they saturate every single last fiber in that system. And you can do that kind of two ways. One is by hand saturation, where you lay it out on a table, you pour out epoxy on the table, place the FRP onto it, pour more epoxy over the top, and you work it in with a plastic putty knife until you've reached that full saturation. And that's obviously a little bit labor intensive, so people have come up with mechanical saturation machines. Are a lot more dependable over time, especially for large applications where you're trying to get a lot of FRP done quickly. A mechanical saturator essentially runs the FRP through a bath of epoxy with rollers that press the epoxy into the fabric itself. If you're looking at quality control in your project, it's very important, or probably a very good idea, to include mechanical saturation as one of your requirements on your specifications. So you've done all the prep, you've sanded down your concrete. You can do that by grinding, shot blasting, or even water blasting. You want to hit that ICRI concrete surface profile level 3. So essentially a flat surface with all of the imperfections removed from the outside of the concrete in an open pore structure. Then you prime the substrate and go back over it with a thickened paste to fill in any imperfections, saturate the fabric, and then you can lay it up, in this case, horizontal loops around the column. Once that's all cured, there's usually some sort of coating requirement that goes on over FRP. If it's in an interior unexposed condition where no one's going to see it, it is perfectly fine to leave completely uncovered. A lot of times on the exterior, UV will start to will not specifically degrade the epoxy, but it will discolor it, and it will cause concern with people that come by and see the product. So a lot of times when it's exterior, you want to coat over it very minimally with paint, just to keep the UV rays off of it, or there's other types of protective coatings that you would want to use for various reasons, right? So if you had, say, chemical exposure or abrasion exposure, you might go over it with an epoxy coating to limit that impact. A lot of times there's aesthetic concerns. People don't want to see the weave of the FRP fabric. We can go over that with a cementitious coating that'll make it look more similar to concrete. That cementitious coating is also used for fire rating at some point, or in some cases. And then we actually have an acrylic paint that we use to go over it in exterior applications, just to try to match aesthetics. And well, if you look on the left, FRP is not the most attractive thing on its own, so a lot of times you end up coating back over it. So again, still technically part of the superstructure, but we're moving out over water at this point. I believe some of this happened over land as well, but we're starting to look at the supporting girders in the vents. Those also needed reinforcing. They didn't have enough bending flexural reinforcement to take the new load, or shear strength to develop that new capacity for the light rail system. Very similar to the previous portion, the EOR was KPFF with Sound Transit and Washington State DOT. The FRP installer was FD Thomas. And this scope we're looking at is strengthening of the existing girders for shear and flexure. So up top here, there is a negative moment deficiency where this portion of the concrete girder here wants to try to dip off of the column and separate, forming a crack up here. So we have longitudinal FRP providing tensile reinforcement up towards the top of the member, and then to reinforce for the shear of that block trying to drop straight down, we have FRP U-wraps that go down the side, around the bottom, and then back up to the top. And that's a very typical way to reinforce a beam for shears with an FRP U-wrap, vertical element coming down, around, and over, very similar to a rebar stirrup. So one way that you can get a little bit better activation of your FRP is to add anchors. So if you're looking down here at the member end section, we have these little anchoring elements. And those are FRP anchors. So bring this photo up. They have an embedded head in this case that goes into the concrete, very similar to an epoxy dowel. And then this fan or tail here gets splayed out, and it would grab that top of the U-wrap and activate the FRP, so you're not depending on it developing across the face. So you end up getting a little bit better activation of your FRP right off the bat by adding an anchor. Anchors are typically added to get load through members, so you could have a double fan ended rope of FRP fiber, basically, that grabs fabric on one side of an element, goes through an element, and then grabs fabric on the other, or these embedded anchors like this. Embedded anchors are also used for load transfer. Sometimes they're used to get a little bit higher strain value out of the FRP, so we can get more capacity out of it, and it really depends on which situation that you're looking at. And great thing about working for Simpson is that's what I'm here for. So you can always reach out to me if you have a project or a question about FRP. My email's in the chat box already, so you can look that up, send me a message, and I'll get back to you as soon as I can with a response. All right, so here's an example of an unreinforced bent over the pontoon portion. So we're up in the substructure, and then I'm just going to step through real quickly what that reinforcement starts to look like. So we have a strip across the top that's taking that positive flexure, kind of holding those two elements from twisting off the top of the column. And then we come back through with the U-wraps that go down vertically. They get anchored off at the top. They would wrap around the bottom of this bent, and that gives you your shear reinforcement. Now we're going to start looking at the actual pontoons and what was done down there. So if you're looking in this photo, the red rectangle I've added, that's the actual pontoon structure that's supporting this bridge out in the middle of the lake. The lake is much too deep to actually bring a full vertical support down to the bottom. So we have a floating bridge that we got to make sure can take the flex of that light rail. So in this photo, we're out over the water still, but I want to reiterate the importance of surface prep and coatings. So if you look at the left here, these guys have already finished their grinding or shot blasting. They've removed that upper layer of concrete and opened up the pore structure, and they're in the process of priming the substrate and going back over it with thickened epoxy paste to fill up all those imperfections. On the right, well, sorry, I got ahead of myself. In this photo, we're just about ready to start applying the FRP. So they would step into saturating it and actually laying it up on the substrate, pressing it into the substrate, and then monitoring it while it cures. They want to monitor it while it cures to make sure it doesn't peel off or cause any delaminations. And while it's still wet, you have a good chance to work any imperfections out of it. So a lot of times you'll want to watch it while it cures all the way through the whole entire process. Once it's cured, you're ready to do your coatings, which I have an example of here on the right. This case, they were just painting over to make it match aesthetically. So you really, if you go out there, you can, if you look very closely, you can start to see the FRP kind of transposed through. But for the most part, the FRP on this project got coated over, and it's going to be very difficult to find unless you know what you're looking for. Kind of stepping a step back from surface preparations, concrete can have a lot of issues, or masonry can have a lot of issues even past just getting the surface flat. There could be spalls, there could be cracks. All of those types of structural deficiencies typically need to be addressed before FRP is applied. So on the left here, we have a team of workers that are doing crack injection. FRP, pretty much any crack over 0.01 inch is going to need to be injected in most cases. And that's because those fibers need to stay in tension. So you can imagine if you apply FRP over a substrate and it has a 1/4 inch crack in it, well, when that crack tries to close up, it's going to push that FRP up into itself, and it's no longer going to be in tension. And that's the reason we need to get all these cracks addressed, is we can't have any gaps under the FRP when it's installed. It has to remain in tension to function properly. Very similar, spalls are something that need to be addressed, or damaged substrate. You got to remove that, replace it, get it back to smooth in order to install your FRP. Ends up being not typically a huge problem for concrete spalls. A lot of times it's just that clear cover depth that's getting removed or spalled off. And in most cases, you can fill that with an epoxy paste. as you're applying the FRP. Our epoxy paste can go up to a 1-inch lift or 1-inch fill, 1-inch spall at a time before it gets over its maximum lift capacity. So you can work with that or a concrete repair mortar to repair all your spalls prior to FRP installation. So the pontoons of the I-90 westbound lanes, they needed post-tensioning strands added to their structures to allow enough flexibility and strength to cope for the new light rail. So as that light rail comes over the pontoon portion, it's going to try to deflect downwards. It might twist a little bit because this light rail system's mounted off to one side of the highway and it's not a very balanced load. So the PT strands are there to try and keep everything under compression as it deflects so the concrete stays in place. And then the nice thing about PT is it functions a lot more like a spring to reorientate the structure back to where it's supposed to be, as long as it's never exceeded its capacity. So these PT strands run through the entire pontoon structure, and the pontoon structure did not have a plan for that originally. So there's lots of concrete bulkheads in the way, and we needed to be able to core new holes in to string the strands through the pontoon structure, and those new holes need FRP or some form of reinforcement around them. FRP was the solution that was chosen on this project. So looking at the left here, you have a PT anchor point into the existing concrete pontoon. On the right-hand side, you're going to see man doors running the length of the pontoons to give you an idea of how long and how many bulkheads we needed to get through with FRP. But like I said, this jack on the left is going to pull those tension strands or pull those strands into tension, and that tension is going to compress the entire structure between anchor points to keep it in compression. That way, as it moves, the concrete stays in compression and the steel takes all the stretch. And that's a very good system for allowing a concrete structure to move and not fall apart. So moving to the next slide. Oh, things are frozen. There we go. The FRP ended up installed inside of these pontoons in a confined space. And if you've ever worked around or dealt with a confined space, VOC content is going to be very important. In the case of the Simpson FRP system, we have very, very, very low VOC content. So workers were able to come in through this little access point, come down in here and work with minimal ventilation and minimal safety equipment. Of course, where what they have to, but very low VOCs, less of a concern than if you were to use maybe an acrylic epoxy or something along those lines. So the FRP fabrics were flexible enough to get through this man door. So that's one of my big selling points for FRP in general that makes it a good solution for projects, is that it can get into those tough to reach places. It's a rolled up fabric. Even after it's saturated, you can re-roll it on the roll, pass it through a small opening. And then when it comes to the actual application, you essentially need enough room to prep the concrete and get your hand in there to install the FRP, and you can still make that installation. So all the FRP in this photo came in through that access hole and was installed down in this confined space. And you can see the horizontal and vertical strips on this wall face are blocking out around these two rectangular sections. And those are the areas that are going to get cut out or cored through for PT strands to string through. So the FRP above and to the sides blocking that out is essentially there to replace any loss of tensile capacity from the rebar that would be in those core locations. So we've cut, coring through this, we're going to cut a few bars here and there, and the FRP is sized to replace that capacity. Just a little bit close up of that installation. And there's two things that I think are important to note when we look at this photo. The first is, if you look very closely, we have this translucent white material around the outside. That is actually the thickened epoxy paste. And that is required around the exterior, any edges and seams of FRP. So that's not sloppy workmanship you're seeing there. That's part of the specification for FRP. This is actually a very, very clean FRP installation. But the reason that you want to feather all those edges is, well, for one, they'll protect the FRP edges during cure and throughout the rest of construction, so nothing catches that edge and starts to peel the FRP. but also they're there holding down the edges of the FRP, preventing stress concentrations from debonding the FRP. So if you had a portion that wasn't feathered, say down at the end of this strip or up at the end of this strip, and the FRP went under load and it wasn't completely feathered out on that edge, you could have a stress concentration that starts to peel the FRP off. It's very important that all the details and specifications are met with FRP and everything's done 100% as required. Secondly is that there is not a coating on this FRP. This is actually the final installed condition. And going back to that coating conversation we had earlier, there's really no need for a coating when you're in an interior location where no one's going to see what your FRP looks like.
Alex, 3 more minutes.
Oh, that's perfect. We only have one more slide. So this is the last slide, and this is where I come in and Simpson Strong-Tie comes in. We're not just a manufacturer. We do provide FRP and composite materials, but we're really an engineering support company. And I'm here specifically to help you out with your projects. It's the whole reason I took the job is I got tired of being at my desk. I wanted to go talk to people, work on interesting things with them. So highly motivated to help out. And we really want to provide you with a world-class engineering support. So our team can provide feasibility studies, budget estimates, help you with your specs, help you with drawings and calculations. We can even provide drawings and calculations stamped and sealed by an engineer from Simpson Strong-Tie. And then down here at the bottom is the one that I might be most proud of. And if you're looking in the background of this slide, you can kind of see our lab. We have the Tygill lab in Stockton. It is basically available to anybody, engineers in the industry, anybody that needs project-specific testing, as long as it's going to make sense for the project and it's an application that's worth pursuing. You can give us a call, talk to us about what you need done, and there's a good chance we're going to be able to pull it off down in our lab. So all of these services are available to you. And really what you need to know leaving here is you can reach out to me at the phone number or email below with any question about FRP or FRCM, which is a whole nother system that we're not going to cover today. And I'll give you as much help as I can. So that's all I had planned for today. I'm going to switch back over to the chat because I'm not sure if I've gotten any questions, but please let me know.
Thank you very much, Alex. I enjoyed your presentation. You don't know how much I enjoyed it. I did something similar 20 years ago on a bridge here in Salt Lake City, and we tested it on the old I-15. But these pictures you put up remind me of that. Of course, at that time, we didn't have anchors. There are some questions here. I can send you the papers. There are some questions here. Do the corners on the existing structure have to be chipped away to provide a rounded profile?
The answer to that is yes and no, actually. So you have to have a 3/4 inch minimum radius. And you can achieve that by chipping it or grinding it away and profiling that edge. Or you can use the thickened epoxy paste to make that profile itself. And actually pulling that off in practicality becomes kind of a challenge because it is a pliable material until it's set up. So you might be able to radius it out really nicely. And then when you actually push the fabric onto it, it could deform a little. So if you were to take that route with the epoxy, you'd want to let it set up a little bit before you went around.
Another question is, how was the discontinuity of the FRP over the cross beams at the connection to take the longitudinal girders mitigated?
Discontinuity of the FRP over the cross beams. You know, let me look back at my photo. I don't remember us actually breaking the FRP. So let me see if I can find that slide.
So while you're looking, I noticed your anchors were at 12 inches. How is that determined, the spacing of the anchors?
So let's see from
the FRP anchors I'm talking about.
Sure. So the FRP anchors, they're going to be, the spacing is not set. It's not, well, we generally follow ACI spacing. So if you were looking at a tie spacing and we had, say, access to 3 sides of a column, but we still needed a closed tie, well, those anchors would be governed by ACI minimum spacings.
Okay.
But in the case of a U-wrap, where we're not actually looking for that, right? The U-wrap itself is providing our strength. So that's going to be a little bit wider strip width. the anchor spacing at that point is really just governed by the strain in the FRP and how much load we can pull into one particular anchor.
Okay, so the question is clarified where the girders rest on the cross beams.
Where the girders rest on the crossbeam. So let me see if I can end my slideshow and then restart it on the right slide. 1 second. So we're looking at this detail here, if I'm not mistaken. Yeah, so this guy, as you can see, we're not actually going, the cross beams on this project don't interfere. But if they had interfered, let me get back to the right screen, say if we were coming in and there was a cross beam kind of perpendicular with this longitudinal and it cut off this longitudinal strip, in that case, we would be looking at the FRP through anchor element where you have a fan on one side, fan on the other, that would grab the right and left of the strip, and then the embedded portion would be hidden within that beam. And that's one approach that we would look at.
Okay, thank you.